In this video, I'm going to discuss inspecting threads and what parameters of threads we're interested in and what gauges we use for thread inspections. For this video, we're going to be using the angle block, so go ahead and either download this print, or if you want to 3D print this or make this on your own, that's fine. Otherwise, just grab any part that has an internal thread and another part that has an external thread. I'm actually going to use a bolt for the external thread part of it and the angle block part for the internal thread. So go grab one of those while you follow along. Preferably what you have thread gauges for, if you know what thread gauges are, if you've already got some thread gauges. But before we get started with the gauges and the inspections, we're going to do a quick screw thread review, and we're going to discuss the parts of the thread that we're interested in as inspectors. For the most part, machining people who are machining these threads and making these threads, they have many more parameters that they're interested in, such as the crest profiles and the shape of the thread, the the thread engagement ratios. I'm not a machinist. There's a lot of parameters that they're interested in. I've simplified this diagram down to just what inspectors are really interested in. And the main one we're interested in is the pitch diameter. The pitch diameter determines the working diameter where the threads mesh together and either lock or roll if it's a rolling thread, a moving assembly. But the pitch diameter is roughly halfway from the bottom to the top of the crest, and it's actually, well, we're going to go into the definition later. I have a picture. Some other parameters that I'll throw out, I'll mention the minor diameter is the smallest diameter that is on the thread, so it'll be from the root to root on both sides, and the major diameter is going to be across the crests on either side. The pitch is going to be how tightly each thread rotation is to the next rotation, how tight that distance is, and we define it as threads per inch. So if it's 16 threads per inch, there's 16 rotations in 1 inch. If it's 10, there's 10 rotations in 1 inch. And then throughout the discussion, I'll be mentioning the root. That's the lowest part of the thread, and the crest is the high part, and the flank is just going to be the side of the thread. This is an example of a 60-degree UN thread. There are many other shapes and profiles that you can apply this discussion to, and they have different shapes. Some of them are square, some of them are trapezoidal, rounded. There's many more out there. So when you come across those types of threads, look that information up, and you'll see most of these same parameters applied to the other styles of thread. We're going to focus on this one because it's the most commonly made. For the internal thread, it's the exact same thing. There's no difference. I'll even flip back and forth between internal and external. The major is still the largest part, but now the root is, I forgot to flip the root and the crest. The root would be down here, and the crest will be up here. But essentially, it's pretty much the same. The pitch diameter is in the same place. The pitch is the difference between the peaks or the valleys, and it's the same terminology. The minor diameter is the smallest diameter, the major diameter is the largest diameter, and the pitch diameter falls in between. So this would be like for a nut or a drilled hole, like on the angle block. So getting down into pitch diameter, like I said, this is, as inspectors, when you're inspecting a thread, this is what we're most interested in. If the pitch diameter is correct, oftentimes all the other parameters of the thread will be correct just because of the way threads are fabricated. It's hard to have the pitch diameter be correct and something else to be wrong. So if the pitch diameter is wrong, many other things are probably wrong as well. So, but they are all important, but we really focus our attention on the pitch diameter. We have pitch diameter gauges. We call them plug gauges and ring gauges. So plug gauges will check holes, and ring gauges will check external threads, such as the bolt we're talking about. And as I mentioned, the pitch diameter is, approximately halfway down the flank, and the actual definition is when, this gap between the crests equals to the crest thickness. So when as you slide up or down, there'll be different thicknesses, but when they're equal, that's where the pitch diameter sits. And we draw these circles to represent where the pitch diameter is. So these are meant to represent like a cylinder sitting in that valley there, right at the pitch diameter. And if you read ANSI ASME Y 14.5 Rule 3, they will go into a little bit more detail, but this is essentially it. Whether it's internal or external, it looks just like this. But for inspectors, we don't really necessarily need to know, this exactly, but it's nice to know what the pitch diameter is, because it's basically about halfway down from the peak to the valley. And actually, I'll say the pitch is the same, no matter whether you go peak to peak, whether you go valley to valley, or whether you're going half pitch is in the valley, or half pitch on the crest. Either way, the flank distances are the same, about halfway down. So screw thread identification. When you're looking at your drawings and your blueprints, they're going to call out in this format. They're going to start off with the diameter, then they're going to give a pitch, then they're going to give a thread series, and then they're going to give the thread class. So 3/8 16 UN 2B, 3/8 is the nominal diameter, 16 pitch, so 16 threads in 1 inch. And when we convert that to a decimal, we just put 1 divided by 16 to get 0.0625. This will come up in some of our calculations later. UN is the thread series, so Unified National, nothing to verify this really. The thread shape, of course, but as we buy thread gauges for 3/8 16 UN, we're going to be verifying that. So 2B and 2A, this is where there's you need to pay a little bit of attention. A B call out is an internal thread. So this tapped hole on the angle block here is called out as a 2B because the B represents internal thread. The A represents external thread. So that might be like the bolt that goes into the hole. So the bolt would be A, the hole will be B. The number 2 is relative to a thread's, jump ahead, a thread class. So when you're talking about 1, 2, or 3, 1 is a loose fit, 2 is a typical fit, and 3 is a tight fit. Whether you're talking about nuts or bolts, internal or external. When you're dealing with tapered threads, you're going to have an MPT series, L1, L2, L3, that follows the same trend. And Acme threads, 1G, 2G, 3G. As you get larger numbers, it gets tighter and tighter fit. So most of your career, you're going to see the class 2, 2A, 2B. That's for most mechanical assembly purposes. Those are fine. You might see 3A and 3B if you're designing a gauge, something that needs really smooth operation. It gives a tighter fit, reduces any looseness that might be in the thread. A lot of gauges, they're going to have a nice smooth thread. So they're not going to be class 2, they're going to be class 3 or even held tighter than that. Jumping back, we talk about our thread series. We have some common ones: UN, UNC, which is Unified National Course, UNF, which is for fine, UNEF, which is extra fine, and UNS is special or non-standard. So there are standards when you talk about matching up a bolt diameter and a pitch. There are standard ones that are commonly available so that they're made in high volume and they're easy to find gauges for because they're made in high volume. But you actually, as as an engineer, as a machine shop, you can make any diameter and any pitch you want. So a lot of them will be special for special applications, and you will define that as UNS. The reason people use special threads is sometimes clearances are tight and maybe the pitch is too coarse or too fine. It doesn't work for them. They need a really specific pitch to make this application work. There's other times where you're using thread as a timing mechanism, and every rotation translates to some mechanical timer, and so you have to control the mechanical timer by controlling the pitch very closely. So you might end up picking a non-standard thread at the diameter you're working at. And there's no universal, standard pitch, because as the diameters change, the standard thread pitches change with them. So in this example, the 3/4, if you're going to be UN, you're 12, 28, and 32. If you're UNC, you're going to be 10. UNF is 16, and UNEF is 20. But in our previous example, our 3/8 16 is a UN, and our UN on a 3/4 are 12, 28, and 32. And our 16 in this case would be a fine. So it changes between different threads. It's really not that critical for you to inspect or verify, because the pitch diameter checks are going to verify everything about this thread. So don't focus so much on that. That should be the last thing you're focusing on. The rest of the thread call out is much more important. 3/8 16 and the class and the internal or the external are much more important. Now, when we talk about how do we inspect thread itself, the pitch diameter, I mentioned we have some specialized gauges, and we have a thread plug gauge and we have thread ring gauges. These gauges come in Go, NoGo applications. So on a thread plug gauge, your Go side should go in the hole and your NoGo side should not. When you're dealing with a plug gauge, out of the way. When you're dealing with a plug gauge, the Go side is typically longer than the NoGo side. That can help you quickly identify it. This body has gotten so used up and worn that it's pretty hard to even see the Go and the NoGo, and it's under this label. But right away you can see the Go side is usually bigger than the NoGo side. For the rings, you're going to have a Go ring and a NoGo ring, and it's the same thing. The Go ring should go on your part, the NoGo ring should not. It's the same as plug gauges. When you're checking holes, you have a Go pin and a NoGo pin. It's the same application. So very quickly I'll demonstrate. I'll put my Go into this 3/8 16 hole on the angle block, and it goes just fine. And then I'm going to take my NoGo and try to thread it in, and it locks right away. I can't do it. So these gauges are designed with different pitch diameters. The Go pitch diameter should go in the hole, and the NoGo pitch diameter should not. So can't even really force it. I definitely don't want to try to force it. You'll damage your thread and you'll damage your gauge. So with my Go ring, I can do the same thing. I can thread the bolt through. There it is, poking through. And then I can grab the NoGo. This is the NoGo right there. And it went a couple of turns, but that's okay. There's usually a lead-in allowance for the first 3 threads. So if you can get 3 turns and stop, you're still passing with a NoGo. Otherwise, if the NoGo goes the entire length of the shaft, then your pitch diameter is out of spec. Oops, a little too far. So let's compare threads and ring gauges. So plug gauges check external threads, ring gauges. Plug gauges check internal threads. This is a typo. Plug gauges check internal threads. Ring gauges check external threads. Plugs are solid pieces. Rings are adjustable. So all of these gauges have a bolt in here that you can adjust slightly to calibrate these gauges to account for a little bit of wear. Eventually the ring gauges wear so much that no matter how much you adjust the tightness of the ring, it can't get back into specification. Let's see. Plug gauges are Class B gauges. So when you look at a plug gauge, I'll try to get it on the camera, you'll see a 2B. Well, it's a little scratched out, but there's a 2B and not a 2A. Try to focus on those. Right there, 2B. And a ring gauge is going to say 2A. And that corresponds to our holes. So our hole for a plug gauge is a 2B hole, so we use a 2B gauge. And for an external thread, we have a 2A thread and a 2A gauge. Now if you have a 2A thread and a 3A gauge, or a 2A gauge and a 3A thread, that may or may not be interchangeable. The numbers when you're dealing with class 2 and class 3 change what's allowable for pitch diameter or not, so you can't always interchange them. But for the most part, they're still going to be very similar, very close, but there'll be minor differences. Oh, and let me show you that bolt while I've got the second camera up. So this gauge, it's exposed. There's a bolt here you can adjust, and another one on this side. Maybe that's a nut. This one's covered in wax so that you can't accidentally damage it. No dirt or debris can get in there, so that's very common as well. So how do you calibrate? So with a plug gauge in-house, you can calibrate with a wire or a pitch mic. You can also send them to external calibration. For a ring gauge, you're going to calibrate with a set plug. So I have a set plug here. Looks exactly like a plug gauge, but it's not. It has different pitch diameter tolerances. And the pitch diameters are, so the Go will go on one side and the NoGo will go on one side. So I'll put up the Go. All right, here we go. So the NoGo should actually thread onto this, and then we're gonna tighten the bolts to make sure that it tightens on. So this is a plug gauge to help you adjust the tightness of the NoGo ring to match what it should feel like on a set plug. The Go side has the same situation. Unfortunately, I have a little bit of a difference. I have a Go pitch diameter 334.4, and here I have a Go pitch diameter 333.7. So this is actually not going to fit on this plug gauge. They must be different classes. I did buy them separately, but it would work just like the NoGo side. You thread it on, you adjust the bolt until the tightness feels just right, and then you thread it off. External companies are actually usually preferred to internal calibrations. For one thing, you've got to get these set plugs calibrated, so you might as well just send the rings out for calibration. And calibrating ring gauges takes a little practice, and the calibration companies have that experience, and not everybody who works with ring gauges does. Generally speaking, let's move on. Plug gauges are more expensive than ring gauges, so sometimes shops will only invest in one plug gauge and they won't invest in the ring gauges. A brand new gauge, oh sorry, that's that plug. A brand new gauge might be about $100, $80 in a standard size, and the rings each might be 150 or 200 for the Go, then another 150 or 200 for the NoGo in standard sizes. And in non-standard sizes, it's cheaper to make a plug than to make a ring, so it gets very expensive. So just keep that in mind when you're tooling up. Sometimes you don't need to purchase the rings because the part you're making is the hole. You're not making the shaft that's threading in there, so you can get away with not having the rings. But if you are making the rings, we have other ways to inspect external threads. So sometimes people use those, which we're going to talk about, instead of purchasing the ring gauges. But the ring gauges are great because you can check the full length of a shaft very quickly. You can check if there's any pinch points, any high spots, any bends in the shaft. You can check the entire thing. With the other methods we're going to talk about, really only check one or two spots on the thread and you assume the rest of the thread follows that passing or failing measurement. Next up on our list, with plug gauges, your Go is smaller than the NoGo, so your Go will go in. And if you're, let's explore that. If your Go, if your Go fits into a hole, that's good, right? Because your Go is smaller than your NoGo. If your NoGo also fits into the hole, your thread is too large, right? Because your NoGo is fitting in. Now at the very beginning, if your Go will not go at all, the thread is too small. And you don't even need to bother with the NoGo. So that's how we screen out holes that are too small and too big with both ends of the gauge. With the ring gauge, the Go is larger than the NoGo because you have the opposite situation. You're cutting away material on a shaft. So you're cutting away, and the thread, the external thread, it will not go into your part, right? It's not going, you keep cutting. And then finally it starts to get in. You say, okay, my Go is going on. Let me check my NoGo. Oh, my NoGo also goes on. So I cut too much of the thread. And the NoGo, which is smaller, is getting onto the thread, which means the thread has been overcut and you can't put material back. So you're going to have to remake that part. But you're looking for that window where the Go starts to go and the NoGo will not. And it's the same thing. It screens out shafts that are too large and too small. So let's continue our discussion. Like I mentioned, it's kind of a summary. The Go must go, the NoGo must not go. It's acceptable for 3 turns on a plug or a ring to have 3 turns of a NoGo and still be acceptable. Now some of your NoGo threads are only 3 or 4 turns to begin with, but we're not so concerned with how many threads are on the NoGo. We're more concerned with how many threads this revolves into. So there's more threads on here than on here. So if you can get to the 7th or 8th thread with the NoGo, your hole is too large. And then in simplest terms, if both gauges go on or both do not, you have a problem. Only one or the other. Only one should go on. It should be the Go. And the gauges themselves are manufactured at the limits of pitch diameter, assuming the gauges are following standard pitch diameter tables. There's many applications for non-standard thread gauges. When you have to deal with plating buildup, sometimes you'll change the pitch diameters to account for plating buildup, or you want a special application, a looser fit or a tighter fit. You can make your own custom ones, but for this video, we're just going to talk about standard situations. That's what most people will be running into. So we're going to take a look at some parameters. because we need to know what we are inspecting. So internal thread hole, your pitch diameter minimum on a 3/8/16 thread, class 2B, pitch diameter minimum 334.4, maximum 340 and 3/10. So you've got about 6,000, 7,000, 6,000ths of difference there. On your external thread, 0.3285 to 0.333, so it's even smaller. For your external, you have a smaller clearance. You have a major diameter minimum, but you don't have a maximum on an internal thread. So with an internal thread, look at our diagram. The major of an internal thread is meaningless, but the minor means something. So when we look at our tolerance, that's why there's no maximum, but there is a minimum. This happens to be 3/8, right? 375 and 3/8. For the external thread, actually your major diameter does have a tolerance, 364.2 to 373.6. Not too critical for us to look at. And then you have minor diameter reference diameters as well. Not too critical. I would simply focus on the pitch diameters. Oops. I think I went one slide too far. So when we're talking about the plug gauge, your Go 0.3344 to 0.3347, right? The tolerance for this plug gauge is only 3/10ths of an inch. 3/10,000ths of an inch. And your NoGo side is 0.3400 to 0.3403. Again, that's only 3/10ths of tolerance. So when you're making these parts, these gauges, the manufacturers are held to a very, very tight tolerance. That's why they're ground to precision diameters. The ring gauges, we take a look at the Go side, 0.3327, 0.3330, 3/10ths of tolerance also. And the NoGo, 0.3285 to 0.3288, 3/10ths of tolerance. So even these rings, that's part of the expense. It's a lot harder to manufacture the rings to a tight tolerance than the plugs. So I mentioned, our thread has a pitch diameter minimum and a maximum, and our gauges have a pitch diameter minimum and a maximum. So there's a little tolerance that the gauge manufacturers are allowed a tolerance to make these. And that tolerance, if you look closely, 0.3403 is right here, 0.3403. And so you lose about 3/10ths of the thread tolerance just to make the gauge. So if the gauge is made at 0.3400, you've actually lost a little bit of your thread tolerance, and that's just the accepted industry standard that the gauge manufacturers need some tolerance, and they rob it from one of the ends of the thread. On the other side, right, you have 0.3330, 0.3330, 0.3285, 0.3285. So you got the same situation. Your Go side, your minimum and your maximum are both being shrunk by 3/10,000ths of an inch to allow the gauge manufacturers a little bit of tolerance. So it's going to be very rare that you happen to get a part that is actually within spec according to the thread parameters, but your gauge is just on the wrong end of the tolerance and there's a little bit of overlap and it doesn't work. That's going to be very rare because of the way this is set up, but it is possible. It is possible you could have a thread right on the edge of tolerance and a gauge right on the edge of tolerance, and they've passed each other and they don't go together. But both of them are within their respective tolerance. But again, very rare. I don't think I've come across it, although I have checked a lot of threads. So let's take a quick calculation. What is the gap between the smallest hole and the largest shaft? So the smallest hole is a 0.3344. The largest shaft is a 0.3330. So you have 1,000th and 4/10 of clearance. So that would be a very tight fit, but it would still go. The gap between the biggest hole and the smallest shaft, it's going to be your loosest fit, is 11 thousandths and 8/10. So if you're just going by feel between parts, you could have a very tight fit with 1,000th of clearance and 4/10, or you could have a loose fit with 11 thousandths and 8/10, and they'd both be in spec, right? You just happen to get the extremes of your tolerances stacked up together. So I know a lot of people have gone by feel, and they say, oh, this feels loose or this feels tight. I think there's something wrong. But, the difference between 1.4 thousandths and 11.8 thousandths is really big when you're just going by feel. So that's why we have the thread gauges, to get away from just going off of feel. And then properly toleranced, the major and the minor diameters should not interfere. I think I have a little typo there that helps mess me up. But let's take a look at this next calculation, the gauge pitch diameters. What if you tried to thread the smallest plug into the largest ring, which would be your go? So what if you tried to thread the go and the go? Well, you should never do this. And if you look at the numbers, it's going to be an interference fit. So if you actually force these two together, more likely you're going to really scrape up the plug. You're going to bend or twist the ring to get them to go together. There'll be a lot of friction and a lot of heat because you've got an interference fit. And so don't ever try to do that. Now you're allowed to, obviously the set plugs and the rings go together, but don't force them if they're not supposed to. But the actual thread plugs for measuring threads should never thread together with a ring gauge. So remember that, if you're going to remember anything. Now when we talk about calibration and wear, the plug gauges, it depends on the material you're checking, but they typically don't wear very much. They're very hard and won't wear, especially when you compare it to the ring gauges. The ring gauges do wear faster, and that's another one of the downsides of ring gauges is I could use a plug for 10 years and never go out of spec, but I could use a ring gauge for 2 years and it wears away, and I'm constantly adjusting it, and to the point where it's worn out of specification. So they tend to wear faster, and they're more expensive. In order to calibrate, as I mentioned, a plug, you can use a pitch micrometer that's calibrated. You can use thread wires and a regular micrometer. We're going to do that in this video. As long as everything's calibrated when you're checking this, you're going to be okay. For the ring gauges, you can use the calibrated set plug, or you can send them out to a lab and have them do it. And like I said, the rings are typically replaced much more often than the plugs when it comes to calibration time. So this is an area to focus on when you're talking about your calibration system. If your rings are constantly going out of specification at calibration time, you have to trace that back to your parts. So you might want to either increase the calibration frequency or invest in multiple gauges that you can check with plugs internally and see if they're worn on your set plugs. But either way, they do wear, so keep that in mind. So now we've talked about thread gauges, thread plugs, and set plugs. Those are the ideal tools to have. This is what you hopefully would love to have for every part you're making, but that's not always the case, especially with external threads. Don't want to buy the ring gauges. One of the nice tools that we have available to us is called thread wires. So you basically are going to use thread wires and an OD mic when you don't have a ring gauge or a pitch mic available. So this is a pitch mic here, And we're going to talk about those in a minute as well. And what we're going to do is we're going to put these wires across the thread. Where'd my bolt go? We're going to rest wires across the thread, and then we're going to measure an outside diameter mic across the wires. So it's going to be bigger than the thread, and we use a formula to convert it to pitch diameter. So what that looks like, you know, your chart, your threads will have a chart. Your wires, I should say, your wires will have a chart to tell you which wires to grab, and then you will hold the wires inside the thread and take a micrometer across those wires. And then there's a formula there you can use. There's actually a few ways you can calculate this, but this is the most basic, common formula available. You take your measurement over wires, which is your, you know, across the outside micrometer. You multiply by this constant times the pitch. So your pitch in decimal format. So for us, it's going to be 1 divided by 16. And then you subtract 3 times the wire diameter. So you have to measure your wire or look at the reference on the chart. But a lot of these sets will actually provide a chart to simplify the math for you. So if you don't want to do that math, a lot of times they do some of the math for you based on the wire size. They just give you a constant to deal with instead of a long formula. So these wires, they come in discrete sizes, discrete sets, but they're designed to work for any pitch. So there's more pitches available than wires. You can go pretty much from like 4 threads per inch up to 80 or more. And this one set looks like it's about, I don't know, 16 different sizes. This one set can handle all of those. Each one of these, you know, for example, we're going to use the 40 thousandths wires, and the 40 thousandths wires works on the 16 and the 14 pitch. So some of these are overlapping use. And just keep in mind the chart, sometimes it works off of the major diameter, and that's one thing that sometimes trips people up because they're not used to working with the major diameter, but sometimes the formula involves using the major diameter. So look at your chart carefully. For example, you can do a target pitch diameter equals your major plus what you add from the chart, and then your pitch diameter equals the measurement over his wires minus the constant. So you can work with it either way. The chart has both options for you. So you know what? Before we even go into this, let's why don't I demonstrate it? So measuring over wires, let me give you a close-up on the wires. So here's the set of wires that come in different sizes. They're labeled. I've already pulled out the 40 thousandths wires to use on our 3/8/16 thread. And if you look at the chart, you'll see 16 pitch. I want to use the 40 thousandths. So I grabbed those already, and I've made myself a little holder to help me. You're also going to need a calibrated micrometer. So this one's in pretty good condition. We're going to use this. And now how we hold these wires on is up to you. There's attachments that you can snap onto your micrometer to hold the wires for you. I've seen people use those. You can use like a heavy grease. A grease will kind of push itself out of the way when it comes time for the micrometer to make contact, but it will hold the wires. If the wires are light enough, it will just hold them in there, so you can put your grease and your wires on and then come across with your OD mic and don't need to hold anything. A machinist friend of mine showed me this trick where if you tape the wires together, it can make it a little bit easier, a little bit cleaner. So we're going to try to do this. So what you need to do is you need to get 2 wires on and then the single wire try to show you before I start measuring. Need to get 2 wires on and then a single wire across it in the middle of the other 2, as close as you can. So that way the micrometer is resting evenly across them. So you're going to do 2 on one side and 1 on the other. And let's see if I can do this on camera. It's hard enough to do when I'm not trying to do it on camera. So I'm going to try to register one side and then bring in the micrometer. Sorry, you're not seeing me struggle properly. So I'm registering on the 2 pins, and well, last pin snuck out. But I'm gonna sneak the last pin in. Oops. Well, good thing I dropped the bolt. Not a gauge. So let's try this again. I really like using the grease because there's less things to hold. But you know, feel free to experiment with what you like. Man. I just did this before the video for practice, and I forget how I was holding everything, but I did get it to work pretty consistently. Let's try it like this. Alright, I know my fingers are in the way. It's going to be hard to see what's going on. I almost had it. Alright, I'm going to struggle with this for a little bit longer, and then if not, I'm going to cut the camera and then just show you how I got it done after the finished product. Oh, I think this... Alright, I think I got it. Alright, so I've got pretty good even pressure on the 2 pins and then the 1 pin. It's a little bit off. I'm gonna... There we go. I'll try to center it. I got my ratchet going. Oops, I'm almost sliding off. Alright, let's check our reading. I'm lined up on the 16, give or take. So at this point, I think I've crushed it a little bit. Oh no, it popped out. So I lost it. So I was at the 16. So I'll put it back to where I had it. Took a good look. It goes a little bit more. So that's how you do it. Let's write down our measurement over wires. I'll give it one last shot. See if I can show it on camera a little better. But I'm at 0.375 plus 16, so 0.385, 0.391 and a half. Let me give it one more shot. I think I was getting the hang of it. This is by far the hardest thing I've tried to do on camera for this video series. So even harder than leveling that lightweight part on the jacks. So if you've got a technique out there you want to share, feel free. Sometimes you can set it down. Maybe that'll help. I don't think that's going to help. Okay, that's not bad. I hope you can see that. I actually feel like this is a better reading than before. It feels snug. It looks like it should. Let's try to look at it. So one wire, it's not quite on center. Oh man, do I even try? I'm going to try to center it. There we go. There, I lost it. Can I get it back? Alright, I saved it. So now I'm at about the 18 and 2/10, let's say. I feel like this is snugger. I don't know what you guys think, but it looks pretty good to me. So I'm going to try to give that a nice view on the camera. The measurement across the wires. All right. Well, I'm happy about that. So we're at 0.375 plus 17, so 0.385. Sorry, 0.392 and a half. So we'll change our number just a little bit. Okay. Oops. So that's our measurement over wires. So let's go through the calculation together to convert that measurement over wires to a pitch diameter. All right. So let's look at the top half first. So our major diameter, if we measure it with a micrometer, let's measure it real quick. Let's see if it matches. It's a little bit less than 370. I'd say about 368. This is a bolt. But to go through that example, we'll use the 370. DW is the wire diameter, so 0.04. The chart correction for a 0.04 is 0.02528. Let's see if that's on the chart. Yep, that's on the chart. If you're looking on the secondary camera, 0.02528 is right on the 16 pitch. And then our target measurement over wires would be the major diameter plus that correction from the chart. So 395.3 was our target, and I ended up with 392.5. So we're pretty close. Now we have a couple methods. We can do the pitch diameter formula, plug all that in. In this example, we plugged in 0.3936 as a measurement over wires, and we ended up with a pitch diameter of 0.3297. So if I do that with our measured pitch diameter, so I am going to do the calculation right here, this line, 0.86603 times 0.0625 minus 3 times 0.040. And then we're going to add my pitch diameter. Oops. .3925. And I get 0.3266. I have different numbers than up on the screen. We could do it the other way. Pitch diameter equals the measurement over the wire minus the constant. So let me write down what we just got with method 1. With method 1, my mathematical formula ended up being 0.3266. And method 2, we're going to do the measurement over the wires minus the constant. So our measurement over wire is 0.3925. The constant is 0.06587. That constant comes from the chart. And that is 0.32663. So flipping back to the secondary camera so you can see my calculations. When I use the long formula that I showed you at the beginning, I get 0.3266. When I use the thread wire constants and charts, when I used 16 pitch, 0.06587 in that formula, I really can't see that, I end up with the same result. So however you want to approach it, feel free to choose what works for you. But be careful not to mix up methods and work with the wrong numbers. And that last tip, measure your wires. Use your mics, actually measure your wires. And when you do these calculations, it might actually improve your accuracy, because these wires actually not made to great accuracy. Sometimes they'll be 1,000th or a 0.5 smaller, and when you throw that into the formulas, it actually has a big effect. So I recommend you measure them if you're really working on something tight tolerance for a thread. So for an external thread, we ended up in the example on the screen here, it ended up with 0.3297. And for our example, we ended up 0.3266 off of the bolt. So let's check, are we in tolerance? And 0.3266 is not in tolerance. However, this is a bolt. It may not be made to class 2 specs, and probably is a class 1 bolt, which would have different numbers. So it doesn't really change anything. We wouldn't apply the wrong specification to a bolt if it's supposed to be class 1. I would need to pull new numbers and get those, because a class 1 is going to be different. All those numbers are specific to the class 2 here. But either way, if I'm treating this as a class 2, it fails. But because I know it's a bolt, I don't actually think it is a class 2. It could be. But in the example I had up in the PowerPoint slides, the part that was made, it's just barely in tolerance. So that 329 does just barely fit out the low end of the tolerance here. So it passes. Alright, so before we move on to pitch micrometers, we're going to take a quick break, reset, and continue. I hope you learned a little bit about using thread wires and how difficult they can be, but they actually are a great tool. Same thing with the thread and the ring gauges. I really like using thread wires, plug gauges, ring gauges. So we're going to continue our discussion in a minute. So why don't you hold on a second? Thanks.